Hello, in this video we're going to be talking about section 13.6 about the tangent function. So we've already talked about two basic trig functions, sine and cosine. And on the unit circle, we can think sine measures the y-coordinate, which is sort of the tallness of the angle, thinking about it in terms of its terminal side. And x is cosine, that's the wideness. But there are other trigonometric functions. And depending upon what we want to do with angles, what we want to measure, sometimes other things besides just sine and cosine are the most important thing, or they make things easier. And after sine and cosine, tangent is the most important trig function to know. So here's our definition. For an angle theta, the tangent of theta is just this ratio. We take sine of theta divided by cosine of theta. Where's my pointer? Here we go. So if you know sine and cosine, you can compute tangent. It's just another thing. And here's a really nice way of thinking about what we're measuring here. Let's imagine our unit circle. Oops. And let's imagine that we have some angle in standard position. Nope. So here's our angle in standard position. Angle theta. Here's the point where the terminal side meets the unit circle. That's x comma y. And what tangent computes is the sine value, which is y, divided by the cosine value, which is x. And in terms of the picture, that's a measure of steepness. Here's the origin at 0, 0. And if I were to ask, that terminal side, how steep is it? You remember from algebra that we measure steepness with a slope. And the way we measure a slope is the change in y-coordinates divided by the change in x-coordinates. And in this case, two of those coordinates are just 0. The others we're just calling x and y. So this is the same thing. So a really useful way of thinking of this is that tangent of an angle is measuring how steep is that terminal side. If it's very steep, it has a big tangent. If it goes downward, it's negative, but it could be big and negative. Right? So tangent is really a measure of steepness, not x and y in isolation, but how x and y are related to each other. So it's nice to have that idea, but also just keep coming back to this definition. The tangent of theta is cosine theta divided by sine theta. If you know those values, you can compute tangent. So if you're doing this on your own, hit pause and compute these values. All right, I've given you a little bit of time. So tangent of theta would be tangent of 60 degrees would be sine of 60 degrees over cosine of 60 degrees. Let me switch this back to a pen. Sine of 60 degrees is root 3 over 2. Cosine is 1/2. And let's try to simplify this. Dividing by a fraction is the same as multiplying by its reciprocal. And this is root 3, which is approximately 1.7. If you imagine a 60-degree angle in standard position, something like so, and you're thinking about the steepness of this terminal side, well, it's reasonably steep. It's taller than it is wide by about a 2-to-1 margin, more like 1.7. Tangent of negative 30 degrees would be the sine of negative 30 degrees over the cosine of negative 30 degrees. That would be negative 1/2 over root 3 over 2. And again, let's try to simplify that. The 2's actually cancel and we get negative 1 over root 3. And I would say that's okay. Formally, we don't like to have radicals and denominators. For tangent values, I'm fine if you leave it like that. Do some basic simplification, get those 2's to cancel. But if you have a root 3 or root 2 in the denominator, that's fine. 240 degrees, let's visualize that one. 90 degrees, another 90 degrees, and another 60 degrees. It's like that. This is where 240 degrees is. The sine is negative root 3 over 2. The cosine is negative 1/2, and that reduces to root 3. This actually has the same steepness as this one. It's pointing in completely the opposite direction, so the steepness or tangent is exactly the same. Tangent of 90 degrees would be sine of 90 degrees over cosine of 90 degrees, which is 1 divided by 0. And this is undefined. So it turns out there's no such thing as tangent of 90 degrees. It would require dividing by 0, which is not allowed. Right, and let's just do a little reminder. 1 over 0 is undefined. Don't say equals undefined like it's a number. It just is undefined. 0 divided by 1, that's 0. Some people get mixed up on this. All right, tangent of 2 pi over 3. We are in radians, but 2 pi over 3 is like this one. Same as 120 degrees. The sine is root 3 over 2. The cosine is negative 1/2, and this reduces to negative root 3. Tangent of pi is, sine of pi over cosine of pi. That's 0 divided by negative 1, which is just 0. Tangent of pi over 4, that's like 45 degrees. The sine of pi over 4 is root 2 over 2. The cosine is also root 2 over 2, and anything divided by itself is 1. Hopefully this makes sense. If we imagine that pi over 4 angle, x and y are completely in balance here. That's a slope of 1. It is just as steep as it is wide. Over here, tangent of negative pi over 2, that points down. The sine of negative pi over 2 is negative 1. The cosine is 0, and we have another example where this is undefined, or you can say does not exist. Something that communicates that there is just no value to this thing. So let's think about this. Can we compute tangent of theta for all values of theta? We just saw some examples where we couldn't. And we can't do that when it would involve dividing by 0. So tangent of theta is undefined if the denominator is equal to 0. So that would mean it's things like 90 degrees, 270 degrees, if you keep going 450 degrees, or the negative versions, or if you do it in radians, something like pi over 2, or negative pi over 2, or 3 pi over 2. It's all of these places that are at the very top or very bottom of the unit circle. That's where we have a problem. This is sometimes referred to as finding a domain. The domain of a function is the set of all acceptable input, and some input just don't make sense for tangent. Just like you can't take the square root of negative 7, you can't take tangent of 90 degrees. Now, how often does tangent repeat? If we think of this in terms of period, sine and cosine, we have to go all the way around the circle. But with tangent, what we noticed is this one here and this one here. If they point in completely opposite directions, they have the same slope and the same tangent. So to go completely opposite is just halfway around the unit circle. So this would be every 180 degrees or every pi radians. You don't have to go all the way around the unit circle to see the pattern repeating. With tangent, it repeats after just halfway across, 180 degrees. And let's just comment on something else related to tangent, right? 89 degrees and 91 degrees. Those are very close together. But what if we try to compute with those? So let me switch to a browser. And so tangent of 89 degrees. And that's approximately 57. Tangent of 91 degrees is approximately negative 57. These are pretty big. Remember, sine and cosine never get bigger than 1. But values of tangent can be very big. What if I did tangent of 89.9 degrees? That's approximately 573. Which is enormous. So what happens with tangent is if we move the angle really, really close to something like 90 degrees, we can get very big values. So that's reflected in what's called the range. Range is the output, and it turns out that every single number you can think of, no matter how big, shows up as the output of tangent if you play around with the angle. So one observation here is that all real numbers occur as output of tangent. This is very different from sine and cosine. With sine and cosine, if you compute sine or compute cosine, your answer is always between -1 and 1. Here, your answer can literally be any number you're thinking of. But tangent is what's called discontinuous. It has this unusual property that you don't see with most functions, where the input are very close together. Right? 89 degrees and 91 degrees are very similar as angle measures, but the output are very different. So one way of thinking of this is to say that just because, well, let's say sometimes similar input values give very different output values. Right. All this talk about domain, range, continuity, we're kind of hinting at some more abstract mathematical concepts that you'll be seeing more of in future years. Okay, but that is the end of this video.